All right, so as I was saying, you don't have to be nervous about this proof work because we're not really doing proofs. We're just trying to show how you can tell if a quadrilateral is actually a parallelogram. A quadrilateral means what? Good, four-sided figure. So there are quite a few ways of telling if a quadrilateral is in fact a parallelogram without knowing that the two opposite sides are parallel. Okay? But this will tell you that you have a parallelogram. So one of the ways is that if both pairs of opposite sides are congruent. Okay, congruent, I've got the congruent markings on here. So if you have a quadrilateral and both pairs of opposite sides are congruent, and you don't even know anything about whether they're parallel or not, you can just automatically know that you've got a parallelogram. Okay, and so that means that AD is congruent to what? AD is congruent to BC, and AB is congruent to BC. So please write those things in.
Come on, bro.
That the quadrilateral is a parallelogram if both pairs of opposite sides are congruent, and it is a parallelogram because we know that these opposite sides are congruent. So that's one way to tell. In addition to just that both pairs of opposite sides are parallel.
Wait, Miss Dowdy?
Yes.
I don't think I got that sheet.
No, I don't think I got one. That's engineering.
Mm-hmm.
Thank you.
You're welcome. Okay, so moving on, there are other ways of telling. We know that parallel is important, but if you happen to know that one side is parallel to the other side and it's also the same length, in other words, congruent, that also tells you that you have a parallelogram. So in this case, I don't know anything about EH and FG, but I can tell that it's a parallelogram because I have one pair that is confirmed to be both. So if EF is congruent to HG and also parallel, that's enough to say that you've got a parallelogram. So you need to fill in those blanks. If we wanted to, we could say EH is parallel to FG as well as congruent. That would be another way of showing it, yes.
Can you go back to the last slide real quick because I didn't have the paper.
Okay, momentarily. Does everybody have this one? No. No. Let me give you a second, and then I'll bounce back.
Come on, bro.
And bouncing back. There you go, Isaiah.
Thank you. What? He's here.
No, Kelly, if you give up on me, you're not to.
Okay, gentlemen, please. Okay, and if you're here, they're going to hear you before they hear me. So I need there to not be any other voices on there. Unless you're asking a good question, please. Okay? Yes. This is the other one.
No,
This one. Yep. All right.
No.
Michael Jefferson.
You have a good, gentlemen? If you have a good question, I'm happy to answer it right now. I've got somebody who needs to write this down. All right, here we go. Another way that you can tell is if both pairs of opposite angles are congruent. Okay, I know that this is just kind of seems like maybe not that big of a deal, but just knowing that you've got both pairs of opposite angles congruent is enough to tell you that a quadrilateral is a parallelogram. So these will be the things that we're looking for in order to say, okay, yeah, we have enough to show that we've got a parallelogram. And maybe doing some problems to go along with them. Okay? It should be a little bit faster to write. So angle I is congruent to angle K, and J is congruent to L. And don't forget that angle symbol that we've used throughout, that we have those. Okay, everybody good? Not yet? And one more that we can tell. We had said before that if you've got a parallelogram, then the, what's that word that means connect here to here? Connect here to here. The word is up there.
Bisect each other.
They do bisect each other, but they're good. The diagonals will bisect each other. So the way that this is different is that if you know that the diagonals bisect each other, then you know you have a parallelogram. Okay, so that would break it down into being that these pieces are equal, these pieces are equal, then you've automatically got a parallelogram. Now that doesn't mean that the diagonals are equal. Okay, the diagonals are equal in a very special type of parallelogram, which we'll get to later, but if anybody just know by instinct, what would be the special case where the diagonals were actually equal to each other? Anybody have any ideas or thoughts? Yes. Square, sure, definitely a square. Or even, not even quite as specific, not a rhombus. A rhombus, they actually could be different sizes, but a rectangle also. Okay, but they all will have the trait where they bisect each other, cut them into two equal pieces. Everybody's got that down? Good. Moving right along. So for these four, we want to think about the things that we have and find out, do we have enough information here to know that we have a parallelogram? All right, in this one right here, is that enough information to show that we have a parallelogram? Yes, definitely. We have one side that is congruent to the other side. It is also parallel. Okay, we know that they're parallel because what is the relationship between these two angles? They are, starts with an S. Supplementary, good. They add up to 180. So these add up to 180. That tells us we've got parallel. They're also congruent. So this one, we can say, yes, we have a parallelogram. This to work out. Okay. Okay, so I got all of my answers there. There we go. Okay, so over here, this one, we've got these are parallel and these are right angles. Is that enough to show that we have a parallelogram?
No.
No, it's not. These are right angles. They're equal to each other. They are supplementary. So that means parallel. But we have nothing to tell us that the top and bottom are congruent. We have nothing to tell us that the left and the right are actually parallel. This angle, even though it's not very well defined, even though the angle is not very well defined here, we don't know if they're right angles or not. There's nothing to tell us. So there is, this one's a no. This one might just be, what's the one that just has one pair of parallel, but it's not a parallelogram? Starts with a T. Yep. Trapezoid. So it might just be a trapezoid. We can't tell without a little bit more information whether this one is a trapezoid or a parallelogram. How about this one? What do we think?
No.
Nope, you're right, it is not. We have two pairs of congruent angles, but they're not opposite angles that are congruent. So this one's congruent to this one's congruent to this one. That would lend itself more to a trapezoid. It's possible, but the only way that this actually could be one is if for some reason these two and these two were all the same. Okay, that would be the only way that we could have these two congruent and these two congruent. So this one's no. It would have to be opposite angles in order to be a parallelogram. This one, well, I have this number figured out here. How would you find out that last number since it's not there on your page? Yes.
Because the 187 is kind of figure to the other side, maybe.
If we knew it was a parallelogram, that would be exactly right. But since we're still trying to figure it out, we can't actually use that yet, but I like your thinking. Yes.
You would add the known sides together and subtract it from 180.
Yes, add them together, but in this case with a triangle, we would definitely subtract from 180. But since it's a quadrilateral, we're subtracting from what number? From 360. Good. Quadrilateral has the sum of the angles being 360. A triangle has the sum of the angles being 180. What's your question? Okay, so now we can use what you said about the opposite angles being congruent. Okay, because if both pairs of opposite angles are congruent, it's a parallelogram. Okay, so good job. Okay, but we had to find that they were first, and so add them up, subtract from 360. That's finding an extra angle in a quadrilateral. They do turn out to be equal. That's enough to make it a parallelogram. So far, so good. All right, so we can't be happy with it all without doing a little bit of algebra. I'm going to make sure everybody's got that written down before we move on. The yeses and the nos and the whys. Okay, gentlemen, you pick your heads up, please. That's one of you. The other of you. Yes, yes. Sir. Pick your head up, please. Thank you. Thank you. All right, so I'm going to copy this over. I'm going to put this over on here so that they can see it. So we can do the work on here as well. All right, so if we need to find out if it's a parallelogram, okay, or we're saying what would these variables have to be if we had a parallelogram, what is one equation that we could set up to help and find either A or find B? Any thoughts? It's a parallelogram. What has to be true about these diagonals? What do they have to do? Opposite angles are congruent, yes.
What's that?
But that's not going to help us on that one.
Bye, girl.
Rick, can you help us out here? Look up here. Okay. So what has to be true? What has to be true about these diagonals?
That's the diagonal.
They are diagonal. What do they have to do to each other? Starts with, yep.
Bisect.
They have to bisect each
You
other.
didn't even give me a chance to answer.
And what does bisect mean?
Cut down the middle.
Cut down the middle. They have to cut each other right down the middle, right? So if they cut each other right down the middle, that means that they cut each other into two equal pieces. So what equation then can we have? Yes, good, thank you. Yes.
2A, I mean 4A
4A.
would be plus 20.
4A, how is 4A related to 20?
Because it's on the same.
Okay, so they're on the same line, right? And it cuts right down the middle.
Oh. Times 2.
Not times 2, although there are 2 of them. Who can help?
Get up and torch.
4A and 20 are related how?
Because, but I don't know how to say it.
Didn't matter.
That's exactly what I wanted you to say. 4A equals 20. Because
Oh.
if they cut each other in half, this part and this part has to
Oh,
be
yeah.
the same. Okay? So 4A equals 20. This is a pretty nice one to solve because then
It's
A
five.
just
A
equals
is
5.
A is 5.
Yep, A is 5. So
Yeah.
that's that one. Okay? A is 5 is one of the answers because it says find the value of each variable. What's our other equation going to look like then?
8b plus 1 equals 7b plus 4.
Okay? 8b plus 1 equals 7b plus 4. And then we need to solve that. So let's think it through.
Let me think.
Do we do
Oh,
7b?
The hands is over here. Yes.
No.
Go ahead.
You can subtract 1 from 4.
Okay, let's do the variables
I know,
first.
I know,
Yes,
I
you
know.
can, but let's do the variables first.
Add or subtract 7b.
Good.
Both sides.
Let's subtract 7b. That will give you 1b plus 1 equals 4. And then we can take away your 1 if you wanted to. You could do that all in one step if you want to. But from what I've found is students are more likely to get it right if they handle the variable first. So here we go. Here's our second answer. B is 3. If we wanted to check it, we could do 8 times 3 is 24 plus 1 is 25. 7 times 3 is 21 plus 4 is 25. That's good. They equal each other. So that's kind of a good way to have in your mind how you could find out if you were right. Okay. Everybody good? Yeah. Good. Good.
You're actually through.
Let's move on. So this is the one we just did. A is 5, B is 3. Then we have this one to deal with. So let's think that through. Save it here. Paste it in so we can see it happening. All right. So once again, we want to see if we've got a parallelogram happening. So what has to be true about these numbers? This one will be a little bit harder to find. Yeah, go ahead.
X plus 15 equals y.
Good. X plus 15 equals y. And what's the other equation?
2x equals y plus 18.
2x equals y plus 18. Okay, so then we need to solve this. Any thoughts on how we could solve this?
Let's see if it's one right. Or no. Or
We-
change or just myself.
Okay, solve for one letter. Yeah, we've got this one's already solved for one letter. Okay, so we need to put x plus 15 needs to go in where the y is. We call that substitution. That's the one method that we did this year. So 2x equals, I'll just do color coding here. I'm putting x plus 15 in where the y is. Plus 18. Okay, so what will we do next?
Yeah.
A little algebra review.
We could just put 15 and 18 together since they're just right here.
Beautiful. 15 and 18 together makes,
Go to the bathroom.
33. Okay, now what?
X equal 33.
X equals 33, good, because when we take away x, we get x equals 33. So we found x, that's good, that's one of our answers. One. And then how do we find the other answer? Yeah, go ahead.
You just plug we put 33 to x from all the equations.
Good. So plug 33 in for x in one of the equations. So this one looks like a perfectly good equation. Y equals x plus 15. So y equals 33 plus 15. That's off the side. So 33 plus 15 equals 48. So there's our second answer. And the directions, I believe, said find the values that would give you those. So you need to plug in, you need to manipulate it a little bit. If you've got an equation in two variables, you can use substitution method to solve it, and then we've got our two answers right there. Okay, good. Here's all the work again for that. If you were asked, so the question was asked, what would the sides be? So in order to find the sides, you would definitely have to plug that in. So yes, if we were trying to find the sides, this would be 66, just like you said, and this would be 48. You can pick the easier ones to do, so we could have that definitely in there. So 66. If the question were to go the extra one, and that's always a good thing, this one is 66 because it's not going to do that. It'll make me go over here. Okay. 48 over here.
I very think you stop
And then
putting
the other one's 66 because it's 2 times 33. What was that question? Slow down a little bit. Okay.
There's a scroll down.
Oh, scroll down. Okay.
Yeah, man. Yeah, man.
Okay. And then the last little bit was just some kind of, when I was doing this lesson, making up the thing a couple of years ago, just a little spiritual insight that dropped in. So we're learning about shapes and how they interact and what's true about them. And then we can take what we learn and then apply it to the next thing. And that's kind of like life, kind of like God. We can learn more and more and more things about him. And then the next thing we encounter, we can apply that and better understand what he's about. Part of the point of Flatland, which I am going to flag back to you, but one of the things in Flatland is that we learned more and more and more as you read through the book. You would learn more and more and more about the different types of shapes. And even as you learn more about the different types of shape, they started applying it to what about if the shapes were just intersections of something bigger in a third dimension that intersected with our world. Okay, so you can imagine that God is so much more vast and big and all-encompassing than the puny little dimension that we get to live in, our three-dimensional world. And think about that. Could God possibly use that part that we can learn about? We can learn about him, the part that fits into what our understanding can be, but understand that he's so much more vast. But as we see different ways that he intersects with our life, we can gain our understanding and get closer and closer and closer to him. So that's just a little spiritual tie-in for the day. And I'm going to say goodbye for now to the basketball team. Bless you. Hope you're having a great trip. And I'll shut this down.